So I'm Phil Daian, I'm from Cornell Tech, and this is joint work with Florian Traumer from Stanford and Lawrence Breidenbach from ETH and Cornell Tech. And we'll be presenting Enter the Hydra today towards principled bug bounties and exploit-resistant smart contracts. So the Hydra is fundamentally a story of Floyd Mayweather. Who is Floyd Mayweather? So ex-boxer Floyd Mayweather. Wait a minute, Phil, ex-boxer? Yeah, that's correct, because Floyd Mayweather's new business is now Floyd Crypto Mayweather. And what he's doing is selling ICOs to stack paper like he is in that photo. So what are these ICOs that Floyd Mayweather is going around promoting? So these are sort of crypto tokens, which are Ethereum contracts that represent sort of small transferable bits of cryptocurrency that are created out of thin air in initial coin offerings, token launches, token generation events, whatever your lawyer wants to call it today. And these are a lot like unregulated VC and kind of like shares, except you don't have to go through any process of convincing someone that you have a business plan or a feasible idea. You just kind of create these tokens and sell them to people. So it's no surprise that since mid-2017, interest in these kinds of tokens has been outstripping early-stage internet VC, and they're very attractive to entrepreneurs. So what are the side effects here? So like we saw in the previous talk, we have a lot of these smart contracts that have astonishing amounts of money and therefore astonishing values per lines of code. So we see from $1 to $15 million per lines of code. And people like the previous speaker make these contracts juicy targets, which really upsets Floyd, who's just trying to make some money. So Floyd is very worried by these previous hacks that we've had, the Dow where $50 million was stolen, a year later 30 million stolen from Parity, from 3 ICOs, and then a month later or 2 months later from the updated contract, $150 million frozen in that multi-signature. So what are we going to do about that? How are we going to help Floyd out? Well, to do that, we got to go back to the future. And I'm not talking about the movie here. I'm talking about this work by Chen and USENIX and Knight Levinson on fault tolerance called Inversion Programming. So Inversion Programming is this idea from the 70s that was used at NASA to design and build rockets, saying essentially that you should achieve fault tolerance and exploit resistance through replication. So if you're sending a space shuttle into space, it's going to be there for a while. You don't want a bit flip or something like that to mean your billion-dollar 30-year mission is toast. So you write 3 copies of your program instead of 1, and you take the majority vote to come up with an output. Then if something goes wrong in one of the copies, your agreed output is still okay. So let's model what this is actually doing, which is a pretty critical part of our work. So what inversion programming actually is a program transformation T that takes these n programs f1 through n and comes up with this new program f star, which is shown here as sort of the boundaries around version 1 through 3, and it just acts as a regular program. All right, I'm going to have 2 slides of some math here, so if you want to tune out, please only tune out for 2 slides. So let I sort of be an ideal program specification. This is conceptual, it doesn't actually exist, so you can't actually write this down on paper or code, but what it sort of means is what the programmer wanted the program to do. And let F be a program. So what is an exploit? An exploit is some input X, like we saw in the previous talk, such that the functionality of the program is not the ideal specification. And the intuition is that any deviation from intended behavior is a potentially serious bug and therefore a security exploit. We can also use this to define the exploit set, which is for a given program F and specification I. What are all the X values that cause these to diverge? So now one last thing we want to define with this is called an exploit gap. So an exploit gap is how we measure the effectiveness of something like inversion programming. And it's the probability in the numerator there that some input sampled from a distribution of inputs will cause an exploit in the exploit set of the union of any of the original programs over the probability that that same input will affect the transformed F star. So the top is exploits against F1, F2, F3, any of these programs, and the bottom is exploits against F star. So if you have a gap greater than 1, that means your transformation is reducing exploits. A gap equal to 1, it's not doing anything, and a gap less than 1, it's making things worse. And the bigger of a gap you have, the more effective of a transformation and the fewer bugs you're going to see in F star. This also captures dependencies among heads because at the top we're looking at exploits sort of in any of these programs in that set. So in the case we looked at before with inversion programming, we actually do have a gap here because there's a bug in F1, but this doesn't affect version 2 or 3, and the output is correct. So that'll contribute to the numerator of our function, but not the denominator, and it'll help boost our exploit gap. So why aren't people using this today? What are the criticisms of this? Why isn't this everywhere? Well, having a strong gap like that actually requires pretty strong independence among the original programs. So correlations really hurt you. If you have 2 different buggy versions, then there's no way the majority is going to be correct because only one of the 3 programs is actually correct. And that's what the Knight Levinson study showed in 1986. So these were some professors that had university students code Pascal programs for given problems and checked whether these programs were independent to the sort of bugs that they intentionally designed the programs to be vulnerable for. And they rejected the hypothesis of full independence at a p level of 5%, meaning that they were confident that the programs were not fully independent. They didn't really go beyond that, and they didn't try to measure what really is the independence, etc. So that was done by Eckhart et al. In 1991 at NASA, where they looked at a bunch of NASA data, and they said, we tried this and it wasn't cost effective. In the worst case, we had 3 versions give us only 4 times fewer errors. And this just wasn't economically effective, because if you want to develop 3 versions with different teams, different languages, etc., you're going to need more than 3 times the cost. You're going to have communication overhead and specification overhead, etc. So we'd rather spend that money rather than getting that 4x gap into things like formal verification, dynamic analysis, etc. But not everything is a space shuttle, so this is sort of one of the fundamental insights of our paper. Not all software actually needs to be available at all times. So when you have a space shuttle control or something like that, it can't give up and say, I don't know. But with a smart contract, we actually can. Oftentimes, like detecting that an exploit has happened and giving up is actually better than sending the attacker your money or doing some other unintended action. And that's why we introduced end-of-end version programming. So what is end-of-end version programming, aka the Hydra Framework? So we're going to take the classic idea of end version programming and we're going to strengthen it by replacing that majority vote with a consensus mechanism. So rather than taking the majority of all the heads, we're going to make sure they agree, and if they don't, we're going to invoke a fault manager that does something safe. Unless all versions agree, abort. So why is this better? Because it trades off essentially availability for correctness. So now if you have a bug in any of your original programs, it could take down your contract by invoking this fault manager, but it won't lead to an exploit in your code. So if you rerun the same exact numbers, the same raw data they had at NASA for NNVP, you find that for 3 copies of the program, you get a gap of 4,409, and for 4 copies, you get a gap of around 34,000. So what that means is if you randomly sample an input that's an exploit, there's only a 1 in 34,000 chance it'll identically affect all 4 copies of your program. And that works because we sort of flip the statistical modeling on its head, and instead of asking, will the majority vote be right, we ask, will there be consensus on a wrong value, which is far less likely. So Hydra creates a strong gap, and how does it do that? Well, if there's a bug in one of the heads, the fault manager is invoked, and serious bugs in one head are now no longer fatal to the entire program. So we analyzed a bunch of smart contracts that have been broken in practice for their friendliness to this technique, and this full analysis is in the appendix of our paper. But we conclude that many of the past hacks that we've seen in practice are Hydra friendly, and oftentimes from simple independence sources. So in the previous talk, they mentioned 4 out of 5 classes of exploits were Solidity specific. Hydra supports multiple programming languages. Any EVM compatible programming language can be used. So oftentimes language independence is a very strong source of creating that exploit gap that we need. All right, so what are we going to do now that we have this great framework and this nice mathematical analysis? We're going to use it to create secure bug bounties. So what are the problems with bug bounties today? These are like critical components of everyone's security policy, but they're actually fundamentally flawed. And they're flawed because they often fail to incentivize disclosure. For example, Apple offers a $200,000 bounty for an iPhone 0-day or jailbreak, whereas Zerodium, a gray market vendor, offers up to 1.5 million. So no economically rational attacker will take the bounty. There's often a time lag between reporting and action, so the company that's paying has no guarantee that weaponization won't occur after the bug is disclosed to them and before they have a chance to patch and analyze it. And last but not least, these guys simply don't always pay, or they don't always pay enough. And if you look in history, there are plenty of complaints by researchers that either they didn't get paid at all or they didn't get paid what they were expecting to. So in our opinion, the perfect bug bounty would have these 3 solutions to these issues. The first one would be high leverage. So we want to provide a small bounty, and we want to incentivize disclosure for a vulnerable and valuable program, like a smart contract. We also want automatic payout, where the hunter need not trust the administrator to pay, and we want that to be censorship resistant and verifiable by all parties. And we want automatic remediation. So we want immediate intervention into affected software, sort of automatically patching and de-weaponizing the vulnerability. So to do that, let's take a look at what bug bounties look like today for a rational attacker. So we have this program, let's say smart contract. It's worth $A. So an attacker here finds an exploit, and they have sort of 2 choices in this bounty model. Either they can attack the contract and take this $A, or they can disclose the exploit and get this $B bounty. So when will they disclose? They'll only disclose if the bounty is more than the value of a contract on purely economically rational terms. And that's no good, because you're not going to be offering a $1 billion bounty for a $1 billion smart contract. It's just not feasible. So with the Hydra framework, what we're able to do is actually leverage our strong exploit gap by creating the following game. let's say the attacker finds a bug for head 1. It's not yet a bug for the full program, and it will invoke the fault manager and abort the program if submitted to the chain. We add this extra action of when the fault manager aborts, also paying the attacker some bounty amount to satisfy the automatic payout and the immediate remediation requirements that we sort of laid out earlier. So what does the attacker's game look like now? The Hydra hacker now has two choices. They can either take this bug in head 1 and bring it to the blockchain and take this $B bounty, or they can attempt to keep hacking and generalize the bug in such a way that it'll exploit all 3 of the copies identically and lead to a full exploit in the contract, gaining them $A. The problem is they're racing against the clock. So this is sort of the core insight of the Hydra paper. It's that honest attackers that are finding these vulnerabilities will submit them immediately to the blockchain, because if they don't, they risk getting preempted by other people like them who will take the $B and won't try to go for the $A. So in sort of the game theoretic equilibrium of this, what happens is immediate and rapid disclosure of bugs for the rational attacker model, which is not something that's sort of achieved in any traditional forms of software. So do we have this high leverage? It turns out with the Hydra framework we do. So there's a proof in our paper that the attacker's game, given our independence assumptions and models, actually looks like this. So basically they have two choices. They can choose to disclose the exploit for B, or they can attack, which will give them an expected payout of A over the gap. And if your gap is much greater than 1, this means your bounty amount A can be actually much lower than the value of your contract. You saw before with the NASA numbers, we had a gap of 34,000. We think this is much better for smart contracts than that. Actually finding that number is future work. So here you're incentivized to disclose if B is greater than A over gap, which is much better. I cheated a little. Actually, it's gap plus 1, but we can safely ignore that because they're such big numbers. So wait a minute, this doesn't make sense. Are we disclosing and not attacking even though we're getting much less than the contract's value? And yeah, that's exactly what we're doing because of this time factor and this competitive nature of the game we're setting up here. And so here's an example. Let's use the NASA gap numbers and look at the Omise Go, which is a token contract that we were describing earlier. That's an approximately $1 billion contract. So if they were to implement their 300-line contract with 4 different copies, they would be able to offer a $30,000 bounty that would, with that exploit gap, incentivize rational attackers to disclose rather than attempt to generalize to the billion-dollar jackpot. So we've sort of ticked all the boxes here. We've induced a very strong exploit gap. We have small bounty amounts that incentivize disclosures for valuable programs. We have automatic payout that's censorship resistant and verifiable. The security proofs of that with the blockchain model are in the paper. And we have automatic remediation because the fault manager is invoked immediately, and it's an either or, bounty is paid and fault manager, or neither. So we've implemented this and deployed it on Ethereum with 3 heads on an ERC20 token contract, similar to one of Floyd's ICOs. And we're currently offering a $1,000 bounty on the blockchain at that address for any bugs in any of our heads. The source code for all that is also available. I'll link you to it a little later. We're also deploying a generalized Monty-Hall game, which generalizes Monty-Hall to a gambling game involving K out of M doors. And that deployment is in progress. It's a little bit more complex than ERC20, which is why we went for it. So how does this actually look like in software? Well, there are sort of 2 main components here. One of them is this meta contract, which takes the role of that fault manager I mentioned earlier. The other thing it does is it proxies and caches external side effects of contracts, for example, calls, delegate calls, anything that could have an effect on the external environment will sort of be proxied by the meta contract, recorded on a tape, only executed once, and then compared for equality across all the heads at the end. In order to proxy these calls automatically through the meta contract, we also have an EVM to EVM transpiler that instruments EVM code to sort of do this proxying. And the full details on that are available in the paper. So unfortunately, we're not able to support all opcodes. As we saw before, some opcodes are code specific, but we do support the vast majority of EVM. And you can essentially just write 4 copies of your program, drop it into the Hydra, and it'll deploy it on chain. We've also made some contributions to the smart contract community. So we've issued the first sort of canonical Viper ERC20 example. That's a new smart contract language that's designed to be more secure than Solidity. And we've also given the first public that I know of 100% coverage test suite of all ERC20 behaviors that works on all 3 versions of our ERC20. So is it practical? As I mentioned before, we don't support everything, but if you look at the actual numbers, by code volume, we support 76% of the contracts on Ethereum mainnet today. And by transaction volume, so in terms of what people are interacting with, we support 61% of all contracts on Ethereum mainnet today. So those would be ideal targets for the Hydra, and they represent multi-billions of dollars of total protected assets. We've also listed here the difficulty of how hard we think it would be to add support for these opcodes. Does it scale? So the question is, I'm going to write 3 programs that's going to be 3 times as expensive, almost. So the red lines here show one-to-one scaling. On the left side here, you have token operations, and on the right side, you have a full Monty-Hall game. And you can see that that Hydra scales a little bit better than one-to-one. And this is because of some subtleties in like static overhead costs on EVM transactions. So it does scale linearly, but with a slope slightly smaller than 1. And this can also depend highly on sort of what you're doing. If you have a lot of external interaction that needs to be mediated by the governor contract, this could potentially be worse than linear. So this is not always, but certainly for most contracts that we see in practice on Ethereum today, this is the kind of scaling that we expect. So is it fair? So is this fair for a bounty hunter? And the answer is yes. So there's a class of attacks known as blockchain front-running that actually turns out to be devastating to the economic game that we've set up, where a bounty hunter submits an exploit to the blockchain, but then evil miners or other evil blockchain actors copy it and submit it. Or even worse, some of these evil actors are sitting on exploits themselves, and as soon as they see that someone commits to claiming a bounty, they rush in with their own exploits and preempt them. So this sort of breaks all of the economic analysis that we have. So we do a security analysis in a very strong adversarial model of the blockchain, and we come up with a countermeasure called Submarine sends that does require a deposit that sort of hides the fact that a bounty hunter is even committing to having discovered an exploit in the first place, and then uses commit reveal to enforce the notion of fairness that we want. So the last thing I'd sort of like to go over is sort of, I guess, a philosophic plea to the community, which is that we've been seeing a lot of interest in smart contracts recently, and certainly for all the reasons we've mentioned, the fact that they're juicy targets, that they have public code, and that they're in an adversarial environment, they're excellent targets to take whatever your favorite security technique is from the old sort of class of systems and just apply it to this new model. And that's great, that's very important work, and certainly we've seen a lot of excellent work in formal verification, in static analysis, and in dynamic analysis of blockchain systems. But I'd also sort of like to spark your imagination and posit that these systems might have novel properties that are just like not achievable at all in classic systems. And we've seen in this presentation the fact that each contract has a very precise and known value has allowed us to set up dynamic bounties that constantly change in value over time, that incentivize economically rational actors in a very strong model of rationality. We've seen both in this talk and the previous talk that in many ways there are rigorous and programmatic and sort of like these Cartesian, as the keynote speaker described, notions of security here to be explored. And also an interesting thing about the Hydra, a system with the Hydra, is that you can derive an exact economic security level for your contract. So in our analysis, $A, which is the value of the contract, is exactly as much security as setting your bounty to $B will give you, assuming your assumptions about independence hold. And these assumptions can be empirically validated over time. So that's something that's not possible with like a power plant or with an election system or any classical system, because there's no notion of sort of how much that system is worth or what an appropriate bounty would even be or who the actors are trying to exploit it and why. So there are many new challenges here. There are also new challenges introduced by the adversarial underlying environment that are completely unique, and I'd be happy to discuss any of those new challenges offline after the talk. All right, so you like the Hydra presentation, you'd like to start hacking on the Hydra or maybe write your own Hydra contract. We've spun up a website at thehydra.io where you can read the paper, you can try the alpha, you can try developing your own Hydra contracts. When our Automagic research prototype code doesn't work, you can come to the chat room and ask us why not, and we'll definitely help you out there. So please go check that out and read more and read the source code and ask questions about the system. Also a plug to IC3, which is sort of the cryptocurrency research initiative that I'm part of. You can find more info on that at initc3.org. We're a cross-disciplinary sort of university blockchain research institute, and we're always looking for more collaborations. And with that, I'll leave you with the obligatory disclaimers and take questions. Thank you.
Hi, I'm David Fiala from Google. Thank you very much for the talk, really interesting. I want to lightly challenge the incentive model.
Please.
A lot of people use shared code, like, just push out your own ERC20 contract from some copied thing. And if only some of those players buy into the Hydra model, anybody that doesn't put some portion of whatever their tokens are into this, would they just be left vulnerable, or does everybody that uses shared code basically have to also agree to put some amount of money into the Hydra? Because otherwise you would take the bounty and then you'd exploit everybody else that didn't pay into like this insurance program, if you will.
Right.
And how do you compute the dynamic costs for every, because maybe somebody doesn't want to agree to that standard percentage of your contract that it costs to be in your insurance program.
Yeah, I totally agree. So the question was that the Hydra sort of analyzed these things in isolation and said that if your system uses the Hydra, you get these guarantees. But maybe your F1 is actually independently deployed as someone else's token contract as sort of a standalone thing that doesn't use the Hydra. And then an attacker can both claim your bounty and exploit this other person's contract, right?
And we also saw that in the previous work, that tiny fraction of unique contracts versus the global number of contracts, which exacerbates it.
Right, yeah. So I think it's an interesting question. Certainly Hydra only provides economic security for contracts that use it, and it might make the security of other contracts worse. So sort of the flip side of that would be someone finding an exploit in the standalone contract, and then they come to your contract and claim the bounty, and you're still happy to pay that because it could have been an exploit in your contract had you just deployed that one version. But in general, I think a lot of these systems that we're seeing, these blockchain systems, when people do incentive analyses and game theoretic analyses, they look at the component in isolation, not sort of the interaction with all the parts, just because it's such a complex environment that it's like not tractable to model. This is even the case for Bitcoin. So all of Bitcoin's security work assumes there are like no competing blockchains. As soon as you have a competing blockchain that's incentivized to attack your system, your entire like sort of Nash equilibrium, your rational behavior changes depending on your relative stake in those two systems. So I think it is true. I don't necessarily feel that bad about maybe people who deploy shoddy code and don't use best practices getting hurt by that, though. It's not much worse than the current status quo. Like an attacker would essentially be able to get the sum of all those contract amounts plus the sum of all the bounties. And since the bounties are much, much smaller than the sum of all the amounts, I don't personally feel it would substantially change the incentives. But that would be a cool thing to model, definitely. Yeah, thanks for the question.
Hi, Michael Clifford Nobles. So the entire thing seems to be predicated on the idea that bounty hunters are economically rational actors and that they can make this computation of like, if I'm probably going to get the $30,000, I'm probably not going to get the $1 billion, so I better take the $30,000.
Mm-hmm.
I'd like to offer a counterexample, the lottery, where people will spend a few dollars, which are almost certainly going to lose, in the hopes of getting some life-changing amount of money. And it seems like this is sort of a lottery sort of situation where the bounties are relatively small and the possible rewards, if you go for all four heads, that's like life-changingly large. So one, I guess I'd be asking is, are bounty hunters actually economically rational? And two, in the case where there's such a disparate, such a big difference between the small reward that they could claim and the life-changing amount that they could possibly get, are they still going to behave that way?
Okay, yeah, that's a great question. So the question is, does the difference between the bounty amount and the total value sort of affect people's rationality in making the decision of whether to pursue the bounty? I think absolutely it does, and there's a lot of work on modeling economically irrational actors out there. I think that's sort of beyond this. We have to sort of assume something, and rather than assuming that they're honest as many bounty programmers do today, I would like to make this slightly stronger assumption, but it's certainly not a perfect one. And maybe you'd want to set your amount conservatively higher than sort of this minimum. So maybe you could say, I could do 30K, but I'd really pay 300 to avoid an exploit, so I'll set it at 10x just to be safe. I think those kinds of safety margins would help. And eventually we'll hopefully see professional actors that harvest these bounties like the Tether guys. Then they don't have to worry about doing it on a test net. They can just go claim the bounties and it'll be all above the board.